Hi all, welcome to the next saga, I guess, in our review session. It's going to be on random variables. I'm Brian, I'm on the CSM new course for CSM, and I'll be walking you through this review on random variables. So, random variables. The reason we decided to include this in the first place is because we just wanted to get you more practice with defining random variables. So, what are random variables in the first place? Random variables, as you may know already, because this does get stressed quite a bit, is a function. It's a function that takes you from the sample space to some value in the reals. So, what does that mean? For example, let's say, I don't know why I drew a circle. Let's say we are throwing a coin, and a coin either comes up heads or tails, and we are playing a game. Game with a friend, such that when you get a head, you get +1. When you get and 0 otherwise. Now in this case, we have the sample space, which is heads and tails, but we actually want to find real number values for it. So in this case, our function random variable is going to say, well, let me make this easy for you. It's going to be +1 if you get a heads, and it's going to be a 0 if it's a tails. So I've defined the entire function for you. So given your sample space, which was h, t, you can get real numbers back. And again, this is going to be a Bernoulli random variable. And we have lots of distributions for these, which we'll cover in the next sections. So let's just go through some questions, which I think are very interesting. I'm going to be going over the first one, but I'm going to skip over the second, because the second is perhaps not as interesting as the first one. And I also think the solutions are very well written for the second one. It really illustrates how to calculate covariance. Now, if you have questions on it, please feel free to post on Piazza and we'll get back to you. But I think it's the first example that really illustrates the power of random variables. So let's read through this question. Suppose I have x1 and x2 and uniform 0, 2, where u represents a uniform distribution, and x1 and x2 are chosen IID. What is expectation of x2 minus x1, the distance of x2 and x1? So let's just clarify a couple terms here. This means IID means it's identical and independently chosen. So x1 and x2 are identical, is chosen from an identical distribution, and they're independently chosen. Very strong assumption that you're going to be seeing a lot. The second part is, I just want to clarify this notation. So this notation says we just want to find the distance between x2 and x1. In this case, x1 and x2 are both just one-dimensional. So we're really just going to get x1 minus x2, the absolute value between x1 and x2, right? Later on, you might see a lot of other things like norms, which get really, really interesting. Okay, so let's just walk through this question. So we have x1 and x2 chosen from a uniform distribution. Now, uniform distribution means, I'm going to draw this out. We have 0 and 2 here, and we just select randomly from anywhere right here. It's going to be a random number from there. and x1 and x2 are also chosen independently. So what does this mean? It means that x1 might be chosen somewhere there, x2 might be chosen somewhere there. In another world, we might get x2 chosen here, x1 chosen here. It doesn't matter, right? But the gist is it's going to be chosen independently, and we just want to find the distance between x1 and x2. Let's just assume for simplicity's sake that x1, let's just assume for simplicity that x1 is less than x2. Now this is going to be a without loss of generality. Again, it's a term you'll see a lot. All it's saying is we can swap x2 and x1 around and it will give us the same strong assumption. So let's just assume that x1 is x2. x1 is less than x2. Now, if x1 is less than x2, notice that we can actually break this apart into 3 sections. So number 1 here, number 2 over here, and number 3 right here. We can break this apart into 3 sections that consist of less than x1, and x is, between x1 and x2, and then greater than x2. So we can separate into 3 separate distinct regions. And what we notice is, well, this is the region we're looking for, x1 and x2, between x1 and x2. We look for the distance in, let's call that region x1, x2, right? Because this is what we're looking for. This is our ultimate goal. And notice that x1 and x2 are chosen identically and IID, and they're uniform throughout 0 and 2. So on expectation, so this is just expectation. It can be chosen anywhere, but on expectation, what we notice is the distance we notice that these 3 sections are going to be equal. So this is going to be like 1/3, this is going to be 1/3, and this part is going to be 1/3 of the entire length, and of the entire length. Just on expectation, because x1 and x2 are uniformly chosen. So on expectation, this is what's going to happen. This is what we expect to happen on average, right? That's what it means to be to have an expectation. So on expectation, we get the expectation of x1 minus x2 is 1/3 of this entire length, which is 2. So we get 2/3 in total. Perfect. So we figured out that without loss of generality, we are just going to assume that x1 is less than x2. We look for this section right here. And this section, we realize because x1 and x2 are uniformly chosen, you're going to get 1/3 on every single space and in every single region. And in every single region, because we just add them up, you're going to get 1/3 of the length, and length is 2 because it goes from 0 to 2, and we get 2/3 in the end. Perfect. So that is what the solution actually suggested as well. And I hope that this diagrammatic point of view just helps you a little more. So thank you for watching this section on random variables, and I'll see you in the next video.